Hey everybody. So today we're going to talk a little bit about kurtosis, and we're also going to introduce a few fun facts about the log normal distribution. So with that, let me get the screen share going. We can get started. All right, so we need to begin by kind of retracting the bit of the last lecture on kurtosis because I was parroting what was in the textbook, but actually the textbook is sort of failing us in a couple of ways with respect to kurtosis. So what exactly am I talking about? So the textbook, as you recall, says that kurtosis is a measure of the peakedness of the underlying PDF of the random variable x. So by peakedness, basically what they mean is that it tells us how peaked the distribution is, how high that, or how sort of concentrated the peak of the distribution is. They also go on to define kurtosis as the fourth central moment of either the continuous or discrete probability distribution, or PMF in this case, or the continuous form. So what do I mean by fourth central moment? Basically, I just mean that we're taking that function x minus the mean raised to the fourth, and we're weighting by the corresponding probabilities, either in discrete space where we're summing over all of the discrete events xi, or in continuous space where we're summing or essentially integrating from minus infinity to infinity the entire domain of the probability density function dx weighted by this weighting this function x minus mu x to the fourth. So anyway, technically speaking, this is actually the fourth central moment, but the textbook said this was the definition of kurtosis. And actually, both of those points are wrong. Both the definition of the kurtosis is incorrect, as well as the physical interpretation. And again, I have Peter Westphal to thank for this because he listened to the video and kindly pointed out that there was a problem. So what is the problem? Again, what the textbook actually defined as kurtosis is just the fourth central moment. Kurtosis is actually the fourth central moment divided by the standard deviation raised to the fourth power. And so essentially, this is not the definition of kurtosis. And I'll show you what is the correct definition of kurtosis in a second. The second problem has to do with the physical interpretation of kurtosis as a measure of peakedness. In fact, kurtosis doesn't really measure peakedness so much as it does tell us something about the probability in the tails of PDFs. And sometimes those are related. So if you have a lot of probability in the tails, sometimes the peaks are sort of more concentrated, but that's not always the case. And Peter Westphal published a paper we'll be looking at a couple of graphs from in a minute, which demonstrate this point. So let's move on from incorrect definitions to correct definitions. So the correct definition of kurtosis given here is kappa, is again that fourth central moment that we talked about a second ago, divided by the standard deviation raised to the fourth power, either expressed for the discrete probability distribution or the continuous form. Sometimes you'll see excess kurtosis, which is just the kurtosis minus 3. Now let me go back to an example that we were working in the last video. So we were talking about the exponential distribution and its application to the specific problem where we had welding machines which only last for some amount of time. And the contention was that the useful life of those welding machines was a random variable, capital T, which has associated with it a probability density function, which follows the exponential distribution right here. So this particular probability density function, or PDF, is characterized by a single parameter, that is lambda. So lambda is the distribution parameter. And one of the things that we showed in the last video is that if you apply the definition of the variance to this exponential distribution and you use integration by parts, you can show that the variance is equal to 1 over lambda squared, or the standard deviation, which is the square root of the variance, is equal to 1 over lambda. And so the standard deviation in this case depends on the distribution parameter lambda. It's the inverse of lambda. Likewise, we used Mathematica because we didn't want to do integration by parts until the cows come home, to calculate the force central moment of the exponential distribution. And when we did that, Mathematica spat out that the answer was 9 over lambda to the fourth. So if we thought this was kurtosis, like the book was telling us, then that would imply that the kurtosis depends on the distribution parameters. So every time you change the distribution parameter, you would actually be changing the kurtosis. But in fact, we know that kurtosis is actually that force central moment divided by sigma to the fourth. So if we take sigma, we raise it to the fourth power and divide it into the central moment, you can see that the lambdas will cancel out. And so in this case, we find that the kurtosis is actually just equal to 9. It doesn't depend on the distribution parameter at all. That's interesting because the distributions themselves look quite different if we plot them for different lambdas. So remember, this is from the last video. So we have essentially 3 different plots using Mathematica, one for lambda equal to 10, lambda equal to 1, and lambda equal to 0.1. And that corresponds to the blue curve for lambda equal to 10, the orange curve for lambda equal to 1, and the green curve for lambda equal to 0.1. And you can see they look quite different. This one obviously looks a lot flatter. This looks maybe more peaked, but in fact, the kurtosis is the same for all 3 of these. Now, you might be able to, you actually can collapse all 3 of these curves through proper scaling. But anyway, the point is that, that in this case, kurtosis is constant. Now, getting to this issue of whether kurtosis is actually a reliable measure of peakedness, Peter Westphal wrote a paper entitled Kurtosis as Peakedness, 1905 to 2014, rest in peace. The idea being that basically this concept that kurtosis tells us something about the peakedness of the distribution has been around for over 100 years, but there's so many counterexamples that it's time to put it to rest. And so one of the pieces of evidence that Peter Westphal offers up is these counterexamples here, where he's plotting the probability density function of the PDF versus X for 3 different distributions: a triangular distribution, one that's more flat, and then one that has these 2 peaks going off to infinity. And the key point is that the kurtosis calculated for all 3 of these distributions is 2.4, when in fact their peaks are quite different. So you can't say that the kurtosis in this case is telling us something so informative about the peaks that they would all look the same if the kurtosis was the same. They look very, very different, yet they all have the same kurtosis. Likewise, you can increase the kurtosis to 6,000, more probability density may be off in the tail, but again, we have exactly the same sort of structure to, well, the same difference between these different distributions, despite the fact that they have the same kurtosis. So anyway, that's kind of all I have to say about kurtosis. So we just need to be careful about the definition. So we just take that force central moment definition in the textbook and divide by sigma to the fourth. And also we need to be wary of how we interpret kurtosis, because there are plenty of cases where it doesn't really tell us much about peakedness. All right, so on to the next topic. I wanted to introduce this concept of a log normal probability density function, or PDF. And the idea is that there are many situations where a random variable conforms to a normal distribution, but only after the random variable has been log transformed. Thus, a log normal PDF is a continuous PDF of a random variable whose logarithm is normally distributed. And in case all those words don't mean much to you, don't worry. We'll work it all out mathematically in a minute. One of the things I want to do to kind of help you through this material is basically contrast 3 different forms of the probability density function, analytical forms. First, the normal PDF for the random variable, which is something we've talked quite a lot about now. The normal PDF of the log transform random variable. So that's something we touched on in class on Monday. And then finally, the log normal PDF of the random variable. And that's something that you haven't seen yet, at least not in this class. And if we're going to be talking about these 3 different types of distributions, we really need some notation so we can keep track of what we're talking about. And so for that normal PDF of the random variable X, we're going to use the capital N to denote normal, and then of the random variable x, given a mean mu x and a standard deviation sigma x. The corresponding PDF or probability density function for that is going to be f sub x, random variable x, evaluated a little x, given the mean and the standard deviation. So this is all stuff you've seen before. The normal PDF of the log transformed random variable x is going to be denoted as, again, the normal distribution, capital N, of the log transformed random variable, natural log x, given two parameters, lambda and zeta. So lambda is called the location parameter, and zeta is called the scale parameter. We'll define those in just a minute. The corresponding probability density function is going to be f of the log transformed random variable x, given a value, specific value of log x, and also given lambda and zeta. Notice that if we compare the normal distribution to the normal PDF of the log transform random variable, look very similar, except x becomes log x, the mean becomes lambda, sigma becomes zeta. And then finally, we can talk about, the log normal PDF of the random variable x. So notice we've kind of switched around the order of words here. So this is the normal PDF of the log transform random variable. And here now it's the log normal PDF of the random variable x. What does that mean? We're talking about the log normal distribution of the random variable x given lambda and zeta. And the key thing that I want to stress is that actually these probability density functions are actually the same. It's just they're plotted differently. So in this case, we're kind of plotting it, think of it as plotting, against natural log of the random variable x. And in this case, we're just plotting it against x. Not really plotting it, but you'll see what I mean in a bit. The PDF for the log normal PDF of the random variable x is denoted by this g sub random variable x evaluated at little x given lambda and zeta. And the reason that, well, by virtue of the fact that these are really the same distributions, just expressed in different ways, explains why it is that we're talking about the same two parameters, lambda and zeta here. Okay, so let's just go through kind of what we already know about the normal distribution, and then sort of apply that to these other two types of log normal distributions that we just mentioned. Okay, for the normal distribution, remember again, we have the shorthand normal distribution of the random variable x given the mean and the standard deviation. The corresponding probability density function we've seen before. So again, it's given in terms of two parameters, the standard deviation sigma x and the mean mu x. So it has these two parameters, which actually happen to be equal to the actual definition of the mean, that is the expected value of x for mu x, and the actual definition of the variance, that is the variance of the random variable x, and that's sigma x squared. I've also added a third parameter here. Obviously, this PDF only depends on two parameters, that is sigma and mu x, but it's important to make a distinction between the variance, which is sigma x squared, versus the standard deviation, which is sigma x. The corresponding cumulative distribution function, or CDF, is capital F of the random variable x evaluated at little x, given the mean mu x and standard deviation sigma x, and it's defined as the integral from minus infinity to that little x, is the upper limit, of the probability density function integrated with respect to, in this case, the dummy variable theta, given mu x and sigma x. And remember, the right way to interpret this integrand here is that we basically sliced up the probability of our distribution into these little dx or d theta slices, and then the probability associated with each of those slices is just the probability density function evaluated at that location times the d theta. If we were interested in understanding the probability of a specific event, say one where the random variable takes on values between a and b, it's just going to be that sort of integration of that differential probability between those 2 points, a and b. That can also be expressed in terms of the CDF which then is going to be evaluated, the CDF is going to be evaluated at B, the upper limit, minus the CDF evaluated at A, the lower limit. And remember, if we convert the arguments of the CDF into the standard normal variate, that is, in this case, take B minus the mean divided by the standard deviation, we can re-express that CDF as the CDF for the standard normal, which is nice because it has a zero mean and unit standard deviation, which we can look up in a table, the corresponding area or probability for. And so then these two CDFs become phi s evaluated in the standard normal variate at B and the standard normal variate at A. And so that's a way of actually determining what that probability of the event of X falling between A and B is. So we should know all that by now. And here's sort of a graphical interpretation just to kind of reinforce those concepts. So what we're doing is we're plotting against X, which has a domain going from minus infinity to positive infinity. We're plotting the probability density function for the normal distribution, fx, evaluated at little x. And that again is denoted by this big N of the random variable x given mu x and sigma x. What are mu x and sigma x? Mu x is going to be the mean, so that's where the peak is. So that's where x equals mu x. And the standard deviation, sigma x, just is a measure of the dispersion around that mean, how wide the distribution is around the mean. If we were interested in the probability associated with a particular value of x sub p, that is the probability that the random variable x is less than or equal to x sub p, that's going to be the area under this curve from x sub p to the left, which is just equal to, by definition, the CDF of the random variable x evaluated at x sub p given mu x and sigma x. Conversely, if we wanted to know the probability that the random variable x is greater than x sub p, we would take the complement of that CDF, or 1 minus that CDF, because we know that the total probability under this curve is 1. So the sum of these two areas, the white slice and the gray slice, have to be equal to 1. And then if we convert that, that x sub p into a standard normal variate s sub p, that's going to be taking x sub p, subtracting the mean and dividing by the standard deviation. Voila, we transform the same problem into now the standard normal variate, which has a mean of 0. So you can see the peak is right at 0 on the s coordinate, and a standard unit standard deviation. And that's denoted here by the capital N01, so 0 mean unit standard deviation. And of course, we can look up in tables what the probability would be associated with this tail right here, or this gray area, because the probability that the random variable s is less than or equal to s sub p is just the CDF for the random normal variate evaluated at s sub p. And the point is that that would be the same as the probability here, that the probability that x is less than or equal to x sub p given mu x and sigma x. So it's a way of calculating this probability without having to evaluate this CDF for every mu x and sigma x. You just make the transform and then look up the CDF evaluated at s sub p for the standard normal variate. Likewise, the complement of that probability is going to be the probability that s is greater than s sub p, and that's just 1 minus that CDF evaluated at s sub p. Okay, so so that's pretty much the entire sort of normal distribution story. Now let's talk about variant, which is this idea that you log transform the random variable, and that is normally distributed. And we call that the normal distribution of the log transformed random variable x. Again, the shorthand is normal distribution of the log transform value of x given lambda and zeta. The corresponding PDF looks like this. So it's essentially exactly what we had for the normal distribution, except that we're replacing the random variable x with natural log of the random variable x. And so that would be true for the variables, or the values that it takes on as well. So this is, instead of x, the natural log of x, given lambda and zeta instead of mean and sigma, or mu and sigma. But other than that, has exactly the same mathematical form. Again, zeta is substituting for sigma, log x is substituting for x, and lambda is substituting for the mean. But other than that, we're looking at exactly the same probability density function. The parameters for this PDF are called the location parameter. That's the lambda value. And the lambda is just the expected value of the log transform random variable. So another way to think of it, since the expected value of this is just the mean of that quantity, the lambda is really the mean of the log transform random variables. It also turns out to be the log of the median value, xm. Remember, the median value is the value of the x-axis of the x-axis where the probability is essentially 50% of the probability is to the left of the value, 50% of the probability is to the right of the value. The scale parameter is zeta squared, and it's the variance of that log transformed x. So it would be the analog of the variance in the normal distribution, but in this case, we're taking the variance of log x, not the variance of x. It's also important to note that this distribution involves just two parameters, that is zeta and lambda, but we can also point out that this median here can be solved for so that the median is equal to the exponential of y. So that's important because we might be given, for example, the median in a problem, and then we would have to calculate the location parameter from that median. And so that's the relationship we would have to use. The corresponding cumulative distribution function is denoted as capital F of the log transform random variable x, evaluated at log x, given lambda and zeta. And that's just going to be the integral from minus infinity up to that natural log x of the PDF. So the only thing that's really interesting here is what we're integrating with respect to. So in the normal distribution, the idea was that we sliced up the PDF into these differential slices of probability, and the value of that differential probability was just the probability density function times dx. But here we're slicing up the probability into logarithmic slices. And so the probability associated with each of those logarithmic slices, indicated by this differential of the log theta, is going to be the probability density function associated with that log theta times d log theta. So it's really the same idea, except that now instead of thinking in terms of x, we're thinking in terms of natural log x. And then if we look at, we're interested in a specific event, so we want to calculate the probability of event, say the probability that the random variable x falls between a and b. You can maybe think about it and realize that that would be the same as the probability that natural log of x is going to fall between natural log a and natural log b. It's really, if natural log x equals natural log a, that means x equals a. Likewise, if natural log x equals natural log b, that means x equals b. So we can rewrite it in this way. And by definition, if this phenomenon that we're interested in is log normally distributed, that means that we can express the PDF as the normal distribution of the log transform values. So we can define that probability then as the integral from log a to log b of the probability density function for the log transform variables evaluated at this dummy variable natural log theta times d log theta given lambda and zeta. We can also express this integral in terms of the two CDFs for the normal distribution of log transform variables, one evaluated at log b, the other one evaluated at log a. And I see there's an error there. That should be subscript log x, not x. And then finally, we can express these two CDFs in terms of the standard normal CDF by just simply calculating the standard normal variate as the natural log of the variable of interest, or the value of interest, in this case b, minus lambda over zeta, and then the same over here for a. Here's some graphical interpretation of what we just talked about. So basically we have the normal distribution again, but instead of the horizontal axis being x, it's natural log x. So after we transform the variable x and by taking the logarithm of it, we end up with a normal distribution. The mean is going to be denoted by the mean of the log transform variable is going to be denoted by lambda. So that's the location where log x equals lambda is going to be the mean of the log transform values. And that's also equal to the log transform of the median value. And again, 50% of the probability under this curve is located to the left of the median, and also 50% of the probability is located to the right of the median. The dispersion around the median value is given by this scale parameter zeta. So that's zeta. And we denote the normal distribution of the log transform value is that capital N of natural log of the random variable given lambda and zeta. And again, we're plotting on the vertical axis here. This curve is basically the probability density function for that normal distribution of log transform value. If we were interested in the probability of a specific event, say natural log x is less than natural log of a specific value xp, which is denoted right here, that would be the CDF of the normal distribution of log transform values evaluated at natural log xp given lambda and zeta, which is by definition equal to the area under this curve to the left of natural log xp. And as I stated before, we can transform that problem here, this probability statement, into standard normal variate by just taking natural log xp, subtracting lambda, and dividing by zeta. And now once we've got it into the standard normal variate space, it's exactly the same story as we had with the regular normal distribution. That is, we're now interested in the probability peak. Let's go back. That's this probability here. It was expressed as probability that natural log of the random variable is less than or equal to natural log of xp. In this space, it's probability that the random variable s is less than or equal to a specific value sp, is given by this formula here. And of course, that's just equal to the CDF of the standard normal variate evaluated at sp, which we can look up in the table. And that's going to give us the probability or the area associated with this part of the PDF here. And just note that the notation here is indicating this is a normal distribution with a mean of 0 and a unit standard deviation. Okay, so we've talked about the normal distribution. We've talked about the normal distribution of the log transform values. And now finally, we're going to talk about the third part of this tripartite set of ideas, and that is the log normal distribution of the random variable x. The shorthand notation is the natural log of the normal distribution, or ln of the random variable x given lambda and zeta. And again, the reason that we have the same lambda and zeta is that really the log normal distribution of x is the same distribution as the normal distribution of the log x. It's just analytically plotted or represented in a different way. And I'll explain that in a second. So the PDF of the log normal distribution of x is given by g of x here, g of the random variable x evaluated at little x given lambda and zeta. So notice that we're not evaluating at log x anymore, we're evaluating it at x. And the PDF itself looks very much like the normal distribution of the log transform variables. It's got that same log x and the lambda and zeta here. The only thing that's new is we've got an x in the denominator here. And I'll explain where that comes from mathematically in a minute. The parameters for this log normal distribution are going to be, well, we can represent it in a couple different ways. Obviously, if we look at the PDF here, it's written in terms of lambda and zeta. So those are the two parameters of the PDF. But we can also think about calculating a mean for this distribution, which would be the expected value of x. And just note that that's not in general going to be equal to the median, which we know from the previous slides is equal to the exponent of lambda. Likewise, we could calculate for this distribution a variance, which is not in general going to be equal to that scale parameter, sorry, zeta squared. And there's only two parameters, so we can represent the parameters in terms of lambda and zeta, or we could potentially represent them in terms of mu x and sigma x and then just calculate lambda and zeta. But we also have this relationship that we talked about earlier, which is the median and its relationship to the location parameter lambda. oops, the corresponding CDF is capital G of the random variable x, evaluated at little x, given lambda and zeta, and that's just equal to the integral 0 to x this time of the PDF g of x evaluated or integrated with respect to theta, which is the dummy variable. Now, here's one big difference between the normal distribution of the log transform random variable x and the log normal distribution of x. Let me just kind of go back for a second. For the CDF of the normal distribution of the log transform value of x, look at the domain. It's from essentially minus infinity to infinity. In case of the CDF, then we would be integrating from minus infinity to some natural log x. If we look at the log normal distribution, however, the domain is from 0 to x. And if you think about it, the log normal distribution or the normal distribution of the log transform values of x, when the log of x is minus infinity, that implies that x is equal to 0. And so that's really the relationship. That's why this lower limit here is 0 for random variable, or the not random variable, but the dummy variable theta. Theta equals 0 when natural log of theta would be minus infinity. So that's kind of the relationship there between the limits of the normal distribution for the log transform random variable x and the log normal distribution expressed as a CDF. Then we can talk about the probability of a specific event, say the probability that the random variable x falls between a and b. Again, that's going to be the probability that the natural log of the random variable falls between natural log a and natural log b, which we can find using the same integration that we used for the normal distribution of log transform x. And that's going to be, we're basically just parroting what we found last time for the normal distribution of the log transform x. So, here's another difference if I just scan back for a second. So we had this picture for the normal PDF of log transform x. So again, log transforming the x, we get a nice symmetrical PDF. Looks like a normal PDF. But if we plot that same distribution against x instead of log x, this is what it looks like. Actually, it can be quite asymmetrical. So here's the case. We've got 3 curves that all have the same median value. So that's equal to 1. And but they have different zeta values or scale parameters ranging from 0.1 to 0.5. And you can see as that zeta value gets larger, the distribution becomes progressively more positively skewed. And so it's a very asymmetrical distribution when plotted in against x, but it becomes a perfectly symmetrical normal distribution when plotted against log x. Okay, so we have a lot of ideas floating around here. One is this idea that the location parameter is the expected value of the natural log of the random variable x. It is also equal to the natural log of the median. But we also know that the log normal distribution has a mean, which is just going to be the expected value of x. And it turns out that the relationship, which I'm not going to prove here, but is in the textbook, or the proof is in the textbook, between these two is given here. So lambda, the location parameter, is equal to natural log of the mean minus the scale parameters divided by 2, or zeta squared over 2. So that's the relationship between lambda, mu, and zeta. Likewise, we can find a relationship between the scale parameters zeta squared and the variance sigma squared. And again, the book proves this formula here, which basically says that the scale parameter is equal to the natural log of 1 plus sigma x over mu x squared. Of course, you recognize that as the coefficient of variation, the COV. And one of the things that we know, if we do a Taylor series expansion on this logarithm expression here on the right-hand side, that when the coefficient of variation is less than or equal to 0.3, zeta simplifies to the coefficient of variation. So if we're given a problem statement that says the coefficient of variation is equal to 0.3 or maybe less than 0.3, we know immediately that that's going to be equal to our zeta if the underlying distribution is log normal. So one of the sort of issues that I left hanging was this relationship between the normal PDF of the log transform X and the log normal PDF of X. So how do we put that extra X in the denominator? Where did that come from? And basically the idea is that these are the same distribution. They're just being expressed differently. They're being, say, plotted differently. And in one case, we're plotting it as differential slices of you know, probability natural log transform X, probability associated with little slices of natural log X. In other cases, we're looking at the probability associated with just differential slices of X. So since they're essentially the same distribution, they have to represent the same differential probability. And that means that the argument of, well, this sort of CDF argument for the normal distribution of the log transform values has to be equal to the CDF argument for the log normal distribution of the random variable. Again, one can think of this as the probability density associated with those logarithmic slices multiplied by a single logarithmic, the thickness of a single logarithmic slice. That gives us that differential probability. It has to be equal to the probability density associated with a differential X because they both represent the same differential probability. Hopefully that was clear. And so we can play a little bit of calculus here. So this d log x here, if we just evaluate the differential of log x, it equals dx over x. And so we can substitute. And we end up with this relationship here. The key point is that we can cancel out dx on both sides and solve for gx. And so our log normal PDF then is equal to the normal PDF of the log transformed x divided by little x. So that's where that extra x comes from in the PDF for G. So this is our kind of master formula relating the two different ways of expressing the PDFs, just as against x or against natural log x. And so if I take my normal distribution of the log transform random variable x, and I apply this formula, so I divide it by x, I get the corresponding log normal distribution of the random variable x, again, given lambda and zeta. And so you can see that x is right there. So that's really how we ended up going from this PDF to the log normal PDF. Okay, so let's do a quick problem to kind of illustrate these points, hopefully. So the problem is as follows. Show that the grain size distribution of sediment in a biofilter, remember we talked about biofilter the first class or the first lecture, when expressed as a probability mass function can be represented equally well by the normal PDF of log transform grain diameters or by the log normal PDF of grain diameters. So, so basically the idea is that, that during one of our field excursions, we actually collected some sediment from a biofilter and we measured its grain size distribution. And so I'm going to show you that data. We essentially fit it to a log normal distribution, and we're representing it in two different ways. One as the normal PDF of the log transform grain diameters, and then again as the log normal PDF of grain diameters. Before I do that, though, I need to tell you a little bit more about the CDF for the normal distribution of log x. So remember the CDF for the normal distribution of log x is expressed this way. So we have this, this integral expression here. This PDF, of course, is given by our normal PDF of the log x. And so I can substitute this expression into the integral. And if I evaluate it, this is what I get. So this would be the CDF evaluated in natural log x given lambda and zeta, which of course is equal to the probability that natural log of the random variable is less than or equal to some specific value of log x. And it's just equal to 1/2 the error function of this argument, lambda x minus lambda over zeta times square root 2 plus 1. So this result here just involves carrying out analytically the integration of this PDF. That's important because I wanted to start by representing the data that we collected from the biofilter in terms of the cumulative probability distribution. So what you're seeing here with the points are are measurements of grain size against, so basically you end up with you get a bucket of sediment, right? It consists of sediment of many different grain sizes. And so what you're looking at is the fraction of that weight that has a grain size equal to a specific value or smaller. So for example, if I look at this point here, basically there looks like there's about an 18% of the mass of that sample had a grain size of 5 microns, log of 5 microns or smaller. Let me repeat that. So the log of the diameter in microns was equal to 5. And for that particular choice of grain diameter, about 15 or 18% of the mass of the sediment was equal to that grain diameter or smaller. Let me put it another way. If we were interested in the median, that is the grain diameter for which 50% of the sediment was smaller in grain size, that would be just coming up here on the CDF at 0.5, coming across to the CDF and then dropping down, and that corresponds to a log transform grain diameter of about 5.8. Anyway, so these points here represent actual experimental data. And what we've done is then fit that CDF for the normal distribution of log transform grain diameter to that data. And you can see the curve there, so it fits the data quite nicely. And when we fit that curve to the data, we end up with the 2 parameter values shown here. So remember, the normal distribution of the log transform values is a 2 parameter distribution. The 2 parameters are lambda and zeta. And so in this case, we're getting lambda is equal to 5.77 and zeta is equal to 0.718. And you can see that lambda equal 5.77 is very close to what I just guessed the median would be. And we know that the log of the median, is equal to lambda. And so that's exactly right. The log of the grain diameter at the median is about 5.8. And that gives us the median right there. So I can equally well represent that same data instead of as a CDF as a PDF. Oops. So here I'm plotting basically a histogram of that grain size distribution, plotted again against log of the grain diameter on the horizontal axis. And then this is the probability density function. Basically taking that same normal distribution of the log transform X values and plotting it as a PDF instead of a CDF. And so this previous curve, which was a CDF, is now represented here as a PDF. And so that's the PDF form. And you could see when these data, which are represented by the histogram, are plotted as against the log of the grain diameter, they do appear roughly symmetrical and kind of follow a normal PDF shape. On the other hand, we could represent that same data instead of log transforming the grain diameter. We could just plot it against the grain diameter, which is shown here. And in this case, you can see the distribution looks very different. Now, most of the probability seems to be smashed up at very small sizes of grain diameter. And then you get this long tail kind of going off into very high or large grain diameters. So I guess and this would be the corresponding PDF for the log normal distribution. That's what it would be called in this case, because we're plotting against the grain diameter, not the log transform grain diameter. And you can see in this particular PDF, we have this extra DG sitting in the denominator right here. So the real point is that these are exactly the same distribution. I'm using the same lambda and zeta values, but they're plotted in 2 different ways. In this log normal distribution, we're plotting it against the grain diameter. And in this normal distribution of the log transform values, we're plotting it against the log of that grain diameter. So, and then representing the CDF in the same way. So these are really the same distribution, just represented in 2 different ways. So hopefully that's clear. And thank you very much for listening, and I'll see you tomorrow.